Hey guys, so welcome back to another stream of Intelligence Maxing, day 47. It's been a month and I think 2 weeks now, so we've been doing pretty well trying to stay consistent with this. And this time, I kind of want to go over some deep learning concepts that I was taking a look at yesterday. Wasn't able to stream it because I was watching some YouTube videos, specifically some YouTube videos by StatQuest, the Josh Starmer guy. He has some pretty helpful videos on kind of the intros to certain types of deep learning architectures. So I created some flashcards. I'm just gonna go through all of them, see what I get wrong, see what I get right, maybe go over some concepts that I might need some help with. Okay, so first question is asking, what is the idea of full zero padding? So I think this concept kind of relates to the idea of convolutional neural networks, and this is a common operation that's used in these neural networks, or specifically these convolutional stages, where you can pad an image with either edges or empty cells or empty pixels or just black pixels or white pixels, so that you can kind of control the spatial dimension. Spatial dimension is just a fancy word for saying the actual size of the image, so the height and the width. And the idea of full zero padding is you pad your image enough so that your actual filter, so the convolutional filter or the kernel, every single cell or pixel or square in our kernel is able to touch every single parts of the image, even the edges of the image. Okay, so I think this picture here is a good representation in the sense that there's a 3x3 kernel here, and then we need to pad our image by 2 on both sides, and in order for us to actually have a feature map that represents every single pixel on the image. And so you can see here that we would probably have a stride of 1 or 2, and this will move our kernel across the image, and then it'll touch every single point on the image. Okay, so I think I'll say that's hard right now, because yeah, I'll put that as hard. Okay, so what is this image showing? Why do the flat rectangles become cubes? The long compared to long. Why do the flat rectangles become cubes, then long rectangles in the bottom half of the image? Okay, I'm not entirely sure what this is saying. I think I might have messed up on the question here. But big idea, this itself represents a convolutional neural network. So we have this, it's read from left to right. 100 by 100 by 3, this represents an image. An image that is 100 pixels width and 100 pixels height, and has 3 different what are called channels. And the way that images are represented in computers usually, they're kind of a 3-dimensional array, or I guess a 2D array, and then each element of the array is going to be a list of 3, or a vector of 3 numbers. And those numbers represent what are called RGB channels. They kind of represent how much of red, green, and blue intensity that single pixel will have. So from here, we have up here a convolutional filter or a kernel, and what's happening is we're going to take this convolutional filter, apply it to this image here, and every single time we apply it, we do an operation called the dot product. And the dot product will take the element by element scalar multiplication, sum everything up together, and then it's just going to output a scalar value. So in this case, our filter is actually 4-dimensional, and the last dimension is k. So k is going to be the dimension of the next layer, which is a fancy word for it is called the feature map. It's just straight up the output of a convolutional stage. So once we have that, we have the same steps over and over again. And the reason why the convolutional filters stay the same, but the actual feature maps kind of get compressed down from a more, I guess you could call this tall and skinny, to a short and fat. Maybe that's the way to describe it. I think the reason is as you compress down these images, but you increase the dimension of the feature map, or the number of channels in the feature map, each channel kind of represents a distinct edge or texture, maybe even color within the image. And so the more channels you have, the more the convolutional neural network is able to learn specific features of the image and be able to make better classifications. I think that's the big idea behind why these start to expand. Represents the filters, kernels, the layers learns, while the bottom half represents the feature maps, each convolutional stage. Okay, so also, right, this is a key thing I kind of missed here, and it's that as you increase the number of channels, the convolutional operation is going to also take more, I guess, there's going to be more steps involved, because you have, let's say, K by M and O and P, which are just all monotonically increasing. Then the number of scalar multiplications you're going to have to do is going to increase as well. It's going to scale with that. So sometimes, like me, I'm a broke college kid, so I don't have a lot of GPU space in order to do all these computations, and so we need to kind of decrease the number of, I guess, the height and the width, and then that, in that case, it'll save some GPU space. All right. Let's see here. So what is the idea of pooling in convolutional neural networks? Okay, so I think the idea of pooling is you kind of reduce the dimension of your spatial map, maybe by aggregating some values. And an example of this, I think a commonly used one, is called max pooling. So you finish your convolution or your dot product, you have a feature map that's 4x4. You might have a 2x2 pooling with, I guess, a stride of 2. Actually, I'm not entirely sure if pooling stages have strides, but if you have a 2x2 pool, then I think you would reduce the dimension of your 4x4 feature map to a 2x2 feature map, or pooled feature map. Okay, what is the idea of a channel? I think a channel is just really a fancy way of saying some type of independent variable, some feature within an image. Some common ones are usually color channels, RG and B. Three-dimensional vectors where each element channel is an RGB value for some pixel. Okay, I think I'll take that. It's not bad. Okay, so what is going on in this picture? All right, this is a bit complex here, but I think what's going on at the end of the day is this is representing a convolutional neural network. Specifically a neural network where we have a feature map that is 224 by 224 by 64, so it has 64 channels, and this feature map is then pooled to reduce the spatial dimension. And you can see in this image we've kind of downsampled or reduced the spatial dimension. I guess you could say this is reducing the resolution of the image, and then we keep the same number of channels. And the way it does that is they're max pooling. So this is, I think, representing an example of not necessarily this image right here, but any image or any feature map that is 4x4, and then we have a 2x2 filter with a stride of 2. So max pooling does have strides. Okay, so we take this and then we stride over, take this block, highest number is 6, this block, highest number is 8, we just pass it over. So the pooling layer downsamples the volume spatially independent in each depth slice of the input volume. Left, in this example, the input volume of size 24 to 24 is pooled with filter size 2, stride 2, into output volume of size 112 by 64. So volume depth is preserved. I think that just refers to the number of channels. Okay, so looks good. Alright, that is easy. So what is a stride? What is its effect on the feature mapping? Okay, so a stride is just a fancy way of saying how far are you going to move your filter on the image. So you could either just move it 1 pixel over, that's a stride of 1. You can move it 2 pixels over, it's a stride of 2, or 3, 4, 5, 6, however long you want. So if you increase the number of strides or the value of the stride, then that effectively decreases your feature mapping, because there's going to be less operations actually computed on your feature map, and the output of each operation represents a single value or single cell on the next feature map. And so if you increase the stride, less computation and less output. Okay, so this is a stride of, okay, so I think what it's trying to illustrate here is that you have a 4x4 image and a 5x5 image. The filter is the same, you have a 3x3 filter, and the feature map is the same. So holding all else constant, the only reason why the feature map here is also the same dimension as the feature map here is because we're shifting our convolutional filter to the right by 2 pixels instead of 1. I think it's pretty good. Okay, spatial invariance. So spatial invariance, this is just a really unnecessarily fancy name, I think. At the core idea, our teacher just said it was the ability to recognize objects regardless of where they're at in a picture. So I think spatial is just representing physical space. Invariance, maybe that's just a fancy word of not caring or no effect. So yeah, I guess maybe the quick and dirty explanation is not being affected by where things are. Okay, it's good. I'd say it's pretty good. Okay, what are some benefits and drawbacks of pooling? Okay, so this is something that I don't fully remember. I want to say maybe the benefits of pooling. This is, I think, a contested topic within the professional or maybe academic space. This is what my teacher claims, so I haven't really done too much digging around here. But I think the idea that pooling helps learn spatial invariance, or the idea that pooling helps with being able to recognize objects regardless of where they are in the image, that is controversial, but some people agree, some people disagree. I think maybe another way of thinking about a benefit is pooling allows you to reduce your spatial dimensions, so that in itself reduces some computational complexity for your model. Drawbacks, maybe it reduces some of the features or some information. You might have a loss of information embedded in, let's say, a higher dimensional spatial image. Higher spatial dimension image. Okay, I'm using all these fancy words, but just having a bigger image, maybe there's a bit more data you can get from the pixels or the feature maps that you have. Okay. Makes training difficult for certain tasks and loses much of information. Yeah, that's fair. So how are images represented in computers, and what is a common way to pre-process an image to be fed as input to your neural network? Okay, so I think images at a basic level, maybe not the most basic, but in a somewhat basic level, they're kind of just like a 2x2 array, or a two-dimensional, not 2x2 array, sorry, two-dimensional array, two-dimensional matrix, and each element within this array or matrix is a vector or a list of 3 values, and those values represent kind of the color channels, the intensity of red, green, or blue. And I think a common way to pre-process an image is to normalize them and then standardize them. So to normalize, I think, really is I mean, maybe the normalization itself is a vague term. I feel like it could represent a lot of things you could do to pre-process an image. What I'm thinking of is to kind of subtract the mean and divide by the standard deviation, so that you kind of get this z-score. I think that's something that we had to do for one of our projects that helped our model be able to train by, I think it's called centering an image, and then I'm not entirely sure what the dividing by standard deviation is called, but that's a technique as well. Then you have different ideas of being able to augment an image, and so you could flip an image, you could expand it, crop it, you could also rotate it, add some noise, meaning maybe you add a few blotches of color. So these are all different types of techniques. Okay, so this is talking about flattening a vector. Okay, that's fair too. I'm gonna put that as hard. Okay, so what does this picture represent? I think this picture is just really representing a convolutional stage and a convnet. Right, so you have the input image and a convolution, so this is the filter, and this is kind of where you actually train your model, and then you have some type of activation, and then spatial pooling, and then all that kind of spits out this feature map. Okay, I think that's pretty easy. Alright. What is this image showing? Why do the flat rectangles become cubes compared to... Oh, okay, I see where I'm going with that. Alright. Okay, so this image is just showing the idea of convolutional neural network, and this convolutional neural network takes in an image that's 100 by 3. It'll apply a filter and output a feature map with k dimensions, and then you notice that these blocks stay the same, 5 by 5 by K, M, N, O. Actually, now that I think about it, maybe these blocks shouldn't stay the same, but they're kind of 4-dimensional, so that I guess they're hard to visualize what they would look like. But big idea, you have your feature maps, they get bigger and bigger and bigger so that you have more channels in order to learn more features, but you want to reduce the spatial dimension because if you kept the same spatial dimensions, it will take up a lot of GPU space in order for you to compute the convolutions or the dot products. And so each of these filters are going to have different dimensions depending on the inputs kernel, not the kernel, but the input feature map and the output feature map. Number of filters increase, the dimension of the feature map, height and width of the image decreases in order to save GPU space. It's operating example. Okay. So idea of full zero padding. Padding is just expanding an image. You maybe add a few pixels to the edge of the image. Full zero padding is just the idea that your filter is able to touch every single point on your image, and in order to do that, you just pad your image by the size of your filter minus one. Excuse me. Okay. How many? What is the padding size? Oh, right. Because I guess it depends on what the actual filter looks like. Because if it's 1 by 1, I mean, in a stride of 1, you can just. Oh. How do we find the padding dimension? So the amounts of padding we should use. The amounts of padding we should use is just the size of the filter minus 1. Okay. Yep, I think it's good. It's the idea of pooling in ConvNets. The idea of pooling just refers to the idea of reducing the spatial dimension of a feature map by aggregating some values. I think the most common one is max pooling, mean pooling. Okay. So what would happen if I initialize all my weights to be a constant? Okay. So I think the thing, if we initialize all the weights to be a constant, then if you were to have, I think, let's say a basic neural network structure that's kind of like a multi-layer perceptron, then you have hidden layers that are connected to each other, and within each hidden layer you have different what are called units or nodes, and if your weights were the same constant, then those individual units will all have the same output because you're multiplying your input by the same value every time. So essentially, instead of having a neuron or a hidden layer that will learn specific things with individual units, that full hidden layer will learn the same exact thing all the time. Okay. Each neuron will receive the same gradient update during back propagation. So happens during back prop. Okay. Oh, what does it mean when someone says that an image has correlated pixels? Teddy bear. Okay. Hey, Beth. Okay, so I think what this is saying, this is a YouTube video I watched with the StatQuest guy. And what he talks about correlated pixels, he's referring to the idea of when you have an image, and specifically he used an example of a teddy bear. If you have a brown pixel, it's likely that the pixels surrounding it are also going to be brown. Unless maybe you're on the edge of the teddy bear, but if you are, I guess in most cases, a brown pixel, then you will have other brown pixels near you. So that's the idea of a correlated pixel, in that usually certain regions of an image will have kind of similar pixels because those pixels represent an object, and I think that's kind of one of the really big drivers of how the convolutional neural network works and why it's used, is because the actual filters, let's say the 3x3 or 4x4, however big filters you use, they kind of take advantage of this correlation idea compared to, I think, a standard neural network with fully connected layers. Each neuron maybe represents a single pixel. Then you're having not only a lot of computations you need to use, but each of these neurons are functioning individually and not realizing the correlation between the pixels. Okay, spatial invariance, again, this is the idea that objects or convolutional neural network will be able to learn to classify an image without caring about where it's at in the image. Recognize that? Regardless of where it appears in an image. What are some benefits and drawbacks of pooling? So some benefits and drawbacks of pooling. Benefits: helps you learn spatial invariance. Will help you also reduce your spatial dimension. Then drawbacks: it's not so great for pixel accuracy models. Also, some people disagree that it actually allows you to learn spatial invariance. And third, I think it loses some information. What are 3 things that CNNs do to help make image classification practical? Okay, so this is going back to that teddy bear example where it allows you to reduce the number of computations compared to a standard fully connected network. It also allows you to learn, or a model to learn, the correlations and take advantage of the correlations between pixels that are nearby. And third, I think it allows you to make classifications even if you were to augment or shift the actual image itself. This one, I'm not entirely sure if, I don't really have the intuition as to why that works. I just gonna take it as it is. And if I have some time later, I'll try to figure out why. So what is the idea of padding? What is zero padding? Okay, padding, you're just adding pixels to an existing image. Zero padding, I actually kind of forgot. I'm not gonna lie. I'm gonna guess that. So full zero padding is when every single piece of our kernel is added to, or piece of our filter touches, or every single piece of our image is touched by a filter. I think maybe it was zero padding. maybe the inputs and the outputs of the input feature map and the output feature map is going to be the same spatial dimension based on the padding that is used. So I think I'm going to go with that. Okay. Oh, the center. Okay, so the center will always touch each pixel. Okay. Yeah, messed that one up, so. What is the common operation used when we apply the filter / kernel onto an image? I think the common operation used is refer to the dot product. Excuse me. Okay. What is a fully connected layer? Fully connected layer, this is just referring to the idea of having, let's say, a n number of neuron in the input layer, m number of neurons in the output layer, and you have a connection between every single inputs in the every single output. You have an n by m matrix to show this relationship. Give an example. Traditional multi-layer perceptron where the layer activations commuted by v times x by m. So n is the number of neurons in the n in this case would be number of neurons in the next layer. X is the number of neurons in the input layer. Okay. Alright, so I'll do hard. Ooh, okay, so explain what is going on in this image. Alright, so this image is going to represent a convolutional neural network. And there's a few steps you need to think about here, but I think at the end of the day, judging from this and this, I think it's a binary classification network trying to classify an image as a 0 or an X. And so this represents a 6x6 image of a 0, and we'll take a filter that is 3x3, and it's learned some parameters. Parameters being you have 1s on the diagonal, 0s on the sides, and then you apply this filter to create a 4x4 feature map. So I think this filter, let's say 1, 2, 3, right, this will have a stride of 1 so that the output dimension is 4x4. Then we feed each element into a ReLU activation, and then we have a max pooling 2x2 with a stride of 2 that will then shrink our feature map to a 2x2 matrix, and then each element will then be multiplied by some type of weight and then aggregated together, then input into another ReLU function, and then multiplied and then added by some scalar value, and then we make the classification if it's equal to 1, greater than 1, or it's equal to 0. Yep. Find and input into new. Okay, I'd say it's pretty good. Okay. trying to see. Okay, I didn't get any updates about something. Okay, so what is the main idea of long short-term memory? Alright, this is where I'm kind of going into uncharted territory here. This is stuff that I haven't really learned about yet in class, or I actually did skip class, so maybe it's something we went over, but just watch the StatQuest videos to kind of get an idea of what's going on. Long short-term memory is kind of a subset of recurrent neural networks. The big idea of these recurrent neural networks is that it'll be able to take in an input of any size. So with convolutional neural networks, with multi-layer perceptrons, the actual size of the input is fixed. They have to be the same. With recurrent neural networks, you can have any sized input you want, and the way that it handles that is something called a feedback loop. The feedback loop is really the idea of copying and pasting your network multiple times, and each time you copy and paste your network, it's using the same parameters, the same weights and bias, just with another input. So one big problem with the recurrent neural networks is that as you increase the number of inputs, then the size of your feedback loop, when you unravel it, gets really high. And so usually what happens is you have an input, you have some type of weight, and then bias, activation, and then you take that output, you feed it back to the previous step, and then put a new input in, and then use the outputs of the previous input to then influence the output of the current input. So that was a bit complex, but once you have the unravel, if you were to copy and paste your network multiple times, each of those networks are connected through this one, I guess you could call connection layer, or connection step. The final output is kind of the product of all of these connection steps, and so the value of your inputs scales exponentially as you increase the number of inputs, and then if your weight is greater than 1, usually this will cause exploding gradients, and if your input is less than 1, then you have the idea of vanishing gradients, because if you have, it's exponentially decreasing. I think long short-term memory tries to maybe then combat this effect by introducing the idea of long-term memory and short-term memory. So I don't fully understand this yet, but I think at a very high level and a basic level, long-term memory are things that a model will store in the long term, and there's short-term memory, which I think are learned from... Okay, I think long-term memory accumulates as you input multiple things into your network. The short-term memory doesn't accumulate and gets reset every time you have some type of input. I could be wrong. Previous inputs and if they're rolled into the next network. Okay. Outputs for previous inputs. Okay, I do have to maybe flag this because it's not super clear what it is, but I'm gonna flag this for now. Okay, so 3 things that convolutional neural networks do to make things practical. I think one big thing, I guess the 3 big things, it allows you to take advantage of pixel correlations. It allows you to make classifications, good classifications, even if you were to shift pixels or transform pixels in your image, and also it allows you to reduce the number of computations necessary in order to make a classification. What does it mean when someone says that an image has correlated pixels? Example of being a teddy bear. I think this refers to the idea that people or pixels in an image that are next to each other tend to be similar objects, or they tend to be the same because most images represent objects and these pixels form an object, and pixels that form an object are all right next to each other. So with the teddy bear, you have brown pixels to represent the actual bear, and if you were to choose pixels nearby, it's likely that the pixels nearby will also be brown because teddy bear is probably pretty big and won't just take a single pixel. Okay. Center of right. So I'm gonna skip this for now. I think maybe go into recurrent networks. So what does a problem does a recurrent neural network solve? Give an example. Contrast this with standard MLP/ConvNets. So this is kind of the thing I was talking about earlier, and that's it tries to solve a problem where you have different sized inputs and you're trying to train a model with different sized inputs. MLPs, ConvNets, they don't allow you to do that. You have to standardize your inputs to make sure that they are the same dimension. And I think one of the examples that Josh Starmer used in his video was the idea of stock prices, and companies have different periods in which they report their stock prices because they get listed on exchange at different times. And so if you were to make predictions using all of the historical stock price data, then you have different sized inputs for different companies. But that's okay because recurrent neural networks solve this problem by introducing the idea of a feedback loop. What is the main idea of a recurrent neural network? How do they work on a high level? Main idea, you can take multiple sized inputs, and the way you could do that is by adding a feedback loop or copy and pasting your layer or your neuron for copy and pasting your neuron. The same weights, but for different inputs. I wonder who came up with this idea actually. Who invented RNNs? Interesting. So it doesn't seem like this is actually seems like this is a pretty old concept. LSTM. Yeah, it's cool. Okay, let's get back on topic. All right. Case value, excuse me, to influence the final output. Okay, so we have yesterday's value, we multiply it by some weights, then we add some sum, put in the ReLU function, and then we connect that to this next, I guess you could call it copied neuron, and we take the value and we add this weight times the ReLU, add those two together, plus 0. Okay. I want to explain what the relationship between these two photos are. So these two photos represent an unraveled recurrent neural network. So basic idea is that this kind of represents the data set that we're working with, and these dots just represent stock prices or stock values. So what we're trying to do here is we're trying to predict tomorrow's value based on today's and yesterday's value. So what we'll do is we'll input yesterday's value. So it'll be 0 times 1.8, which is 0. We add that to just 0, and then we will then put that into an activation, and then this will get fed back all the way back to this sum stage, and then we can also continue to get the value predicted for yesterday. Now, the value that we output from this y1 here is just 0 for yesterday, and then we input the value for today. So the value for today is also 0, so we go through all the steps, then we reach to here, we get the value from yesterday by y1, and then we multiply that by our weight, so we get this is 0 times negative 0.5, then 0 times 1.8, it's also equal to 0, then we add 0, and then we get the value predicted for today. This is the exact same step where instead of combining all of this into a single line, we're kind of breaking this down and unraveling the feedback loop so that yesterday is a single line, and today is a single line, but we connect the different, I guess you could call these neurons, by this connection here that represents the influence of yesterday's value on today's value. And so I think the things we actually learn here are the connection layers, and I think these connections are going to be the same for all inputs.
Yeah, it's crazy. It's a fucking mess. It's a shitty system. Yeah. Yeah, basically. They have to meet for every bill like 4 times. There's so much.
The RNN is an unraveled form that does the exact same mathematical operation. It's a connection between two networks. Okay. Right, this should be the same. So W2 is going to be the same every time. Alright. Go hard. When unrolling in RNN, what happens to the parameters, weights and biases, any effects on model training? So, the same parameters. Each neuron or each copied neuron is going to have the exact same parameters. And so this helps simplify training. You don't have hundreds, thousands of parameters as you increase the number of inputs. Okay, that's good. So the exploding and vanishing gradient problem in recurrent neural networks. So that really has to come down with the whole feedback loop and unraveling process that recurrent neural network has. So if you saw in the previous pictures, we saw that the feedback loop is kind of connecting the previous inputs to the current inputs. And if you were to scale or increase the number of inputs, then you're going to have multiple repeated multiplications of W2 or some type of weights on the previous input. And so this multiplication can grow exponentially as you increase the number of inputs linearly. And that causes, if you have a weight that's usually greater than 1, our input to explode, and if you have a weight that's less than 1, our input to pretty much vanish. Okay, so I think with that, let's try to go over the long short-term memory, and then after I get through these, I might just watch the last video on the transformer stuff, see where that goes. I think that's 107. I have class in about an hour, so I'm gonna try to. All right, let's just try to get this done. So long short-term memory. Main idea, trying to fix the problem of vanishing and exploding gradients. How do you do that? Long-term and short-term memory. Long-term memory, I think, is stuff that is stored within a neuron that helps influence the decisions of short-term memory, which is kind of like the last output of our recurrent neural network. I think if we were to make an analogy between the two, or maybe try to make some connections, long-term memory could be maybe the influence of each input on the actual short-term or the last copied neuron. So yeah, this one I'm a bit shaky on. I'm still gonna save it for later. Alright, so what does the first stage of a LSTM neural unit do? What does it usually refer to? How does it work? Okay, so really a long short-term memory neural units, it's composed of really 3 different stages. So I think the first stage is often referred to as the forget gate, and it really is trying to figure out how much of the long-term memory we should store within this neuron. And the way you do that, I think, is by using the sigmoid function. So there's 2 important functions we need to use in these neural units. First one is sigmoid, second is tanh, the hyperbolic tangent function. They have really similar properties, except sigmoid is between 0 and 1, tanh is between -1 and 1. So the first stage, we're going to use the sigmoid function, and we're going to take our short-term memory and our input to our neural unit, and we're going to do some type of operations on the two. We feed them into a sigmoid function. That's going to give us a value from 0 and 1. We then multiply this value to the actual long-term memory value, and we can think of as the sigmoid output as a % of the long-term memory that we should keep within this neural unit. So that's why kind of the big idea here is the forget gate. How much is the long-term memory going to be remembered? Okay, so this is what I was talking about earlier. You have a sigmoid function. It's kind of the big idea here. You also have an input short-term memory, and you want to be able to pass some type of, maybe you have a weight vector that you multiply to the inputs and also short-term memory. Then you add some bias, feed that into activation sigmoid, and that'll give you a %. what are the two portions of the second stage in a LSTM neural unit? What is this commonly referred to? Okay, so this I think is commonly referred to as the input gate, and there's two portions here that we should really think about. And the first one is going to involve the tanh function. It's how much or what portion of our input should we actually save into what should we actually save into long-term memory? And then I think the second part is what portion of the value we should save into long-term memory should we actually save? Okay, so that's good. I think that's all of the flashcards I have today for the stuff I didn't really learn. I think what I'm going to do now is probably end the stream here and just take a look at some of the videos that StatQuest has on these topics. And with that, I will see you guys in the next one.